In this video we will look at hypothesis testing, and it is very important that before you view this video that you have gone over the lecture notes involving hypothesis testing and looked at a textbook chapter on hypothesis testing as well. You need to know the terms that I'm going to be talking about using in these hypothesis tests. For example, level of significance, hypothesis statement, p-value, type 1 error, even type 2 error, things like that. You need to know what those are, and those are discussed in the lecture notes. And what this video will do is just take all that information and basically just go through the steps of hypothesis testing that I want you to follow, the 1 through 5 steps that I have laid out for you in the notes. And obviously there's quite a few examples of problems that you can look at in the notes as well. So this is just basically doing that, but just actually, where a case where you can kind of see the steps laid out, hopefully. So in this particular case, we're going to test to see if body temperature is really 98.6. Okay, that's been long established, and we're going to use some sample data. This is actual data that was used, that was collected on 130 individuals, and we're going to use that to see if we would support or reject the hypothesis that the mean body temperature of individuals is 98.6. So we will test this at the 0.05 level of significance. So hopefully you understand the idea of level of significance. That's probability of a type 1 error. So make sure you understand that. And hopefully, that there are different types of hypothesis statements to choose from. There's nothing directional here. There's nothing arguing for greater than 98.6 or less than. So we're just going to say mu is equal to 98.6. Mu is not equal to 98.6. Okay, so that's our hypothesis statement. Our test statistic is either a z or a t, and to be a z we need to know sigma. Well, there's no indication that we know what the population standard deviation is, so we're going to have to use the sample standard deviation. So that leads us to a t, and assuming normality here, we then we'll have a t test statistic, which I call t star, is equal to the sample mean minus the hypothesized mean divided by the standard error of the sample mean, so of x bar. So that's what we identify as our test statistic. We won't put any numbers in there. We're just going to identify the test statistic formula. And then in step 3 we need to come up with a decision rule. Okay, well, that's based on alpha, or our level of significance, 0.05, and it can be based on n as well. And in this case, degrees of freedom are 129. So because of that, because degrees of freedom are greater than 30, we can actually use a z to approximate the t. This won't be in a t-table. The t-table that you have in the textbook, once it gets above 30, it starts skipping around, and it doesn't have 129 in there. But we know that any degrees of freedom over 30 we can approximate using the z. And so if I go to the z table and look at look for 0.475, because it's a two-tailed test, so I've got 0.025 area to the right, I've got 0.025 area to the left, so that leaves between 0 and the positive z an area of 0.475. So when I look that up, I get 1.96. Since it's a two-tailed test, it's plus and minus 1.96. So if t star is less than or equal to a minus 1.96 or greater than or equal to a positive 1.96, reject h naught at an alpha of 0.05. Now if we wanted to be more exact, we could use this statement here, and we would be a little different, but you can see the 1.96 does a pretty good job of approximating the exact t-value that at 129 degrees of freedom. Okay, so we're going to go with the 1.96. You do need to use the z-table and the t-table because we're not always going to have Excel available to us. So let's go with the 1.96. Assume we don't have Excel, and so we have this statement here. So that's our decision rule. If t star is less than or equal to minus 1.96 or greater than or equal to a positive 1.96, reject h naught at an alpha of 0.05. Okay, so then we find the mean from these values here, and we find the standard deviation from these values, and we get 98.25 for the mean, 0.733 for the standard deviation, the sample standard deviation, and so then that leads us to a standard error then of s over the square root of n. Okay, so standard error of 0.064. So now what I can do is find out how many standard deviations x bar is from the hypothesized mean. So I take x bar minus the hypothesized mean divided by the standard error, and I get a pretty big number in absolute terms, a minus 5.45. That's telling me that this sample mean here is about 5.5 standard deviations below the hypothesized mean. And here we are using something closer to 2, plus or minus 2, as our cutoff. So there's quite a bit of difference between, statistically speaking, between the x bar and the hypothesized mean of 98.6. So that falls below the minus 1.96. So it's less than minus 1.96. Therefore, we reject h naught and an alpha of 0.05. Okay, so we are rejecting this hypothesis of a mean of 98.6. And our conclusion here is that in alpha 0.05 we have sufficient evidence to claim the average body temperature differs from 98.6. It was found average temperature to be lower. If you find a difference on a two-tailed test, don't forget to then indicate which direction. Okay, because if you make this conclusion, the reader, you're basically leaving the reader hanging, right? You're just he or she's okay. It's different from 98.6, but it obviously would be helpful to know which direction, because in theory they won't see any of this here. They would just look at your conclusion, and so you have to help them out. So you get it was found to be lower than 98.6. Okay. Now remember, it's important again to have looked at the notes first, because you have to have an understanding of p-value. I'm not going to go through all the ins and outs of p-value in the video. You can get that from the lecture notes. But we do have a couple of different ways of figuring out the p-value. Now here it's pretty straightforward, because this is so huge here, again in absolute terms, that it's basically zero. Anything over, I don't like the fact that the textbook stopped at 3.09 in their z-table, but they did, so that's what we'll go with. So anything beyond 3.09 or minus 3.09, we're just going to say has an area of 0 beyond that. So obviously at a minus 5.45, we don't even need to look things up. We'll just say p-value is 0. Okay, and remember, for a two-tailed test, you find the area that's beyond minus 5.45 and then multiply that area by 2, but 0 times 2 is obviously 0. So okay, and then put that in your conclusion. If you do end up with being asked to calculate a p-value, make sure you put that in your conclusion. So then the reader can also make their own decision based on the p-value. So let's say that p-value was 0.02. Okay, we rejected the null hypothesis at 0.05. But if the p-value is 0.02, someone who wants to do the test at 0.01 would actually not reject it. They would fail to reject the null. So listing the p-value gives other individuals a chance to make their own decision, and it's helpful then to provide that if we can. So that's a hypothesis test. Be able to go through the 5 steps. Make sure you know whether it's a two-tailed test or something else. Make sure you know whether you're going to use a Z or a T. Okay, and then just kind of go through from there. Know what your alpha is and come up with the appropriate decision rule, and then come up with your test statistic value, your T star in this case, and make the appropriate conclusion. And then for small sample hypothesis test, let's say we have a city official claims the average cost of a July 4th fireworks display for small towns in the Midwest is less than $8,000. A recent study of 18 small towns found the mean cost to be $6,870 with a standard deviation of 1,700. Test at the 0.01 level of significance to see if the city official's claim is supported. So there's a directional claim there, less than 8,000. So that's our hypothesis. Mu is less than 8,000. That's our alternative hypothesis. Mu is less than 8,000. Okay, because of this directional. Now, you'll see in the notes again that what we're going to do for this class, for showers, is always have the strict inequality in the alternative. So if this had said, and this is the weakness of that particular rule, if this had said test, let's see, display of small towns in the Midwest is no more than $8,000. So now that includes 8,000. Okay, so now that's less than or equal to, so that would be in the null. So no more than 8,000 says less than or equal to 8,000. Well, okay, that's fine, but that becomes the null hypothesis, and it's a very different test then. And then of course you'd be testing against greater than 8,000. So that's the flaw in that particular rule, but it's got more benefits than not, and so we're gonna stick with that rule, and it helps you. It should help you set up the hypothesis. As long as you remember that this has always got to be a strict inequality, then it should, no matter how it's written up here, it should help you lay this out. So this is always going to be either not equal to, a less than, or a greater than for the null hypothesis. Okay. So again, we don't know sigma. This number here came from the sample, so we have a t again. We're going to assume normality, and we have alpha 0.01. That's our pre-sampling probability of a type 1 error. N is 18, so degrees of freedom are 17. So there's no z approximation going on here. We have to go to the z table, and so go to so now in the I'm sorry, did I say z table? Go to the t table, and now go up to, instead of confidence level, go to 1 tail, and then take that row, go over to 0.01. Okay, as long as you stay in that row of 1 tail, go over to 0.01, down to 17 degrees of freedom, and then you've got minus 2.5669. And so now you've got a decision rule that should be stated as, if T star is less than or equal to a minus 2.5669, reject H naught at an alpha 0.01. Okay, so it's a larger number here than the previous example, and that's because we are testing at 0.01, whereas the other problem it was at 0.05, and we have a lot less degrees of freedom here, 129 versus 17. So it's not surprising that we're going to have to show a much greater distance between the sample mean and the hypothesized mean before we're willing to reject the hypothesized value. So let's see what happens. If you got an X bar of 6870, an S of 1700, and a standard error of 1700 over the square root of 18, and so our 6870 minus 8000 divided by the 400.69 gives us a minus 2.82. So that is less than a minus 2.5669, so we reject the null hypothesis at an alpha of 0.05. Okay, now we can't go to the z-table and find p-value. If we wanted to find a p-value, then we would have to have access to Excel, or maybe your calculator would do it. But you could use the t-dist, plug in minus 2.82, plug in 17 degrees of freedom, and because this is a lower tail test, just type in true for cumulative, and you would have your p-value. That is the area to the left of this number right here, 2.82. Okay, and so that we could state that in the conclusion and let people make their own decision based on their p-value. You know, somebody who's really conservative could have 0.001 as their alpha, and so if that were the case, then that would be a situation where they would not reject the null hypothesis. But we did. We rejected the null. We have sufficient evidence to claim the average cost of fireworks display is less than 8,000, but that was all based on an alpha of 0.01. So if somebody wants to use a 0.001, then because it's less than 0.0059, we would that particular person would not agree with us. They would fail to reject. Okay. Again, p-value is explained in the notes, so make sure that you understand how to use the p-value and understand how to calculate a p-value, and both of those are provided in the lecture notes. So if you have any questions, the next video will deal with proportion, and so it'll be some similar procedures here. That we'll still do a 5-step process, but and we'll also go through using the p-value approach in that video as well. So if you have any questions, just let me know.